Okay, very good. So I think now we're moving to considering functions on Riemann surfaces. I should say between Riemann surfaces. Okay, so if you have two Riemann surfaces x and y, you want to define the appropriate functions from x to y, and these functions are called holomorphic. For example, there is also meromorphic functions that I will define soon. So what is a holomorphic function? I mean, as you can imagine, so this is a manifold, a complex manifold. It's a complex manifold. So a function like that should respect the complex structures, right? So what we demand is that for any p in x, and then local coordinates P belonging to you inside X, and such that f of P also belongs. Oh, that's pretty bad. Yes, f of P belongs to B inside Y. This function, so we have this coordinates u and phi for x, and then b and psi. So this is coordinates on x, this is coordinates, holomorphic coordinates on y around these corresponding points. So it should be that, so if you move everything, so here is picture perhaps. So this is F. So this is y, this is x, okay. So you have these coordinates phi here and this coordinate map psi. You get map here. So this map obviously is, so the map that you have is phi inverse composed with f composed with psi. So this goes from, for example, you can imagine goes from, sorry, phi of u to psi of v. This should be holomorphic. So that's a condition. So the situation is that if you come down as a map from some open subset of C to open subset of C, I mean to C, it should be a holomorphic map as we know it for all coordinate charts. And in fact, it is also true that if you check this for one coordinate chart, it's going to be okay for all coordinate charts. So you don't have to worry about checking the condition for all possible coordinate charts, which is, of course, an absolutely impossible task to do. But if you just check it for one, then you know that by compatibility, by transition functions, you're sure that it's true for all coordinate charts. So that's pretty straightforward. Perhaps I should have said here that to start with, we demand f to be continuous, because we want to start pullback of this open set here to be open here, and then check the condition. But this is pretty much what it is. Another thing that we want now is the idea of meromorphic function. So this is f. So somehow from, I just say f from x to c, but then I write it like this. I don't mean that f is defined everywhere on C. So we just say that f is meromorphic around P. So if the following holds, if you choose the coordinates like that, okay, so let me be more precise. F is defined from U, take away P to C, where U inside X is open and P belongs to U. So so your function now is going into C, not going to another Riemann surface. It's just going into complex plane, and it's not defined at P, but is defined in a neighborhood around P. So it's holomorphic. On U, take away E, and if you write, so if you write in its coordinates, composed with phi inverse, again, you just have this coordinate system. So this is something like phi of P. You just, so this is now F, for example. If you do this, then in this coordinate, so this goes from from phi of U, take away P, to C. So this function is meromorphic at phi of P. So what does meromorphic function means? From complex analysis, again, from very basic complex analysis, you know that if you have a function which is holomorphic in some disk around this point, you can always write there is a Laurent series. So the function, any function which is holomorphic in some punctured disk, you can always write it as A and Zn. Right? You can always write it like that. But now, what entails meromorphicity or defines meromorphicity for us is that these negative coefficients are all zero except for a finite number of them. So this is a general. But meromorphic really means the following, that sigma an Zn n from minus n to infinity. So this is called meromorphic. Right? So these are meromorphic. And the smallest n, such that an is different from zero, is called the order of the pole of the function. So this, you can write it as a minus n. I don't know, maybe I just write it as a minus n to Zn plus a minus n plus 1 Zn minus 1, so on. So this, we call this as a pole of order n. So we just say that F as pole of order n. I mean, this need not be negative. I mean, the function could start from some positive power. In that case, is actually holomorphic, right? So, so I mean, holomorphic functions also are absorbed by the idea of meromorphic, but sometimes we just assume by meromorphicity means that there is the actual pole at that point. But what we don't want is to have all the negative coefficients all the way up to minus infinity time to time. We don't want that, because that means there is an essential singularity at that point, and we don't like essential singularity. For the study session, for Riemann surfaces, essential singularities are kind of no. Okay, so we have the idea of holomorphic functions, meromorphic functions, and so yeah, let's define now the order of function at point P, which basically is this number n that I defined over there. So order P, so F goes from U, take away P, which is inside X to C, right? So we just, so this number N, where the smallest number, which is AN, is different from 0, this is called the order of, it's called the order of the function. So if the order of F at P bigger than or equal to 0, if and only if F is holomorphic at P, and in that case, this is actually and is 0. Well, not necessarily. So order of P of F equal to 0 if and only F of P is equal to 0.
It's not equal to 0?
Oh, different from 0, yes. Excellent, different from 0. And order of F at P bigger than 0 if and only F of P is equal to 0, and this is the order of the 0, basically. And this is really the order of the 0, and order of EF negative means that it has a pole of order of P. So these are the kind of concepts that we just take from complex analysis. And then there are some obvious things you have to do. For example, you have to check that this definition is independent of the choice of coordinates. And you can check that. So check that this, because, you know, honestly, to define the order, we have to use a coordinate system. But to do that, we have to make sure that this is independent of choice of coordinates. But this you can do. That's not difficult. Order of PF is well defined. So that's it's independent of choice of coordinates. So that's not a problem. Now let's look at some examples, some simple examples. For example, let's look at what are meromorphic functions on. So here is, this is meromorphic functions on Riemann sphere. Right. So what are meromorphic functions on Riemann sphere? So I want a function from C hat to C, which is meromorphic. So what are some possibilities that comes to your mind, for example? Sorry? 1 over Z? Yes, absolutely. Rational functions, yes. Anything else?
Polynomials? Polynomials?
Polynomials also examples of rational functions. With denominator is 1, yeah. What else?
How can polynomials, because polynomials at infinity are infinity, right? So how are they from C hat to C?
I just wanted meromorphic functions. You know, in the definition of meromorphic, I allow to be infinite. So, okay. Yeah, but okay, so yeah, so indeed, rational functions. So what is this? This is R of Z. This is equal to a polynomial divided by a polynomial, right? Okay. So if you look at, for example, zeros of this, so now you can write it in the following form: product of Z minus alpha I to Ni. So these alpha i's are distinct roots of Z, P of Z. You can just write it. And this one for the denominator, pi, product of z minus beta j to mj. Right? So if you write it like that, now you can see that where are the zeros and where are the poles of the function, right? So what are the zeros of this function, for example? So obviously, I'm assuming alpha I is different from beta j, and alpha I is also different from alpha j, and beta I is different from beta j. So these are distinct roots, but you allow multiplicities. Alpha I, so the alpha I has multiplicity and I, beta j has multiplicity and mj, right? So what are the zeros of this function now? These are these points, alpha i's are the zeros, right? And what is the order of this function, of this function at alpha I, at this zero? It's the multiplicity of the root, which is mi. And what are the poles? The poles are here. The poles, so these are zeros. These are poles. And what are the poles? Poles are beta j's, and order of f at beta j. What is that?
Negative.
It should be negative. Yes, exactly. Negative j. Okay. What else? Did we study all points? Is that it? Yeah, we have to also study infinity, what's happening at infinity. So what is the order of this guy at infinity now? Is it max?
The maximum.
No, order is something.
Yeah, it's just sigma and I minus sigma.
The sum of the orders with should be 0.
Yeah, it should be sum of mj's and take away nj's. Yeah. So this is sum of mj's minus sum of nj's. So if you count everything, you notice that sum of orders of f at p belonging to c hat is equal to 0. So the sums of orders of f at everything. And in fact, one of the first things that we will prove is that this is true for all Riemann surfaces. So in fact, later we'll see that for any compact Riemann surface, and for any meromorphic function f from x to c meromorphic, sum order p of f, p belonging to x is equal to 0. That's a very interesting identity. Okay, so but this comes later on. We have to prove some theorems. Not too difficult, but we need to see something first, and then. Okay, so now what is the other interesting question you can ask about this meromorphic functions on C hat? Sorry?
Could you repeat? Could you repeat?
Clearly, I'm sorry. I'm getting old. My hearing is defective.
Could you repeat?
Oh yeah. So the question is, what is the more interesting? What are some of the other interesting questions about meromorphic functions on C hat? Do you understand me? So,
Are these all of them?
exactly, that's the question. I mean, for any Riemann surface, a very important question is find all meromorphic functions on that Riemann surface. And C hat is the simplest compact Riemann surface that we are studying. So are there any others? So any others? Are there any other meromorphic functions on C hat? The answer is no. These are all of them, and this is not difficult to prove. So let's try to see why this is the case. So, lemma, immediately, because that's not difficult. Actually, for any meromorphic from C hat to C, there exists R of Z rational equal to P of Z over Q of Z, such that okay, so such that f of f is equal to P over Q. When I said this is not too difficult, I was a bit exaggerating because we have to still use something. Okay, so what we are going to do with this meromorphic f from C hat to this to show something like this.
So one thing that we can do is if we consider that the only pole is at infinity, then it has to be a polynomial, because if we write the power series, it has to end so that it's not an essential singularity.
That's right. Yeah, yeah. You can use that argument, and then you reduce to some complex analysis fact. But I was also thinking of making an argument like this, basically. So the argument would be, but you have to allow that there are. I mean, allowing poles at infinity only is too much.
Yeah.
So that doesn't work.
That's
basically
a small part.
That's a very small case because you're allowing all poles to be away except just one, which is not. But you can argue like this. This function f has some zeros and poles. I mean, from basic results, which I haven't proved yet technically, but it's not difficult to see. We'll see it soon. Is that the set of zeros is discrete, the set of poles is also discrete, and there is some finite multiplicity at each, right? So basically I'm saying let alpha I, beta j be equal to zeros and poles of f with multiplicity. I just use multiplicity ni for zeros and beta j and j for this, right? And then you just form this function. Let R of z be equal to be equal to this product of z minus alpha I over product of z minus beta j. I mean, here we have got so ni and j. And then what you can do, you can divide your f by this function, by r. And if you look at this function, you notice that this function has no zero, has no poles, basically. It's a holomorphic function because all possibilities you have killed by dividing. So no poles. Okay, I mean, this is maybe this is a bit too early to say this, but I want to give you some ideas so that we will move to that, maybe prove it more correctly. But no poles. And then very soon, actually, in a couple of maybe.
But it's constant.
Huh?
Why is it true that it has no poles on?
Oh yeah, because where the poles could be, because you're dividing should be zeros of this. But the zeros cancel each other because this function has exactly the same number of zeros and same number of poles as f.
Oh.
So they cancel each other when you divide, right? So it has no poles on C. So this is holomorphic. Now, very soon I will prove that any holomorphic function on a compact Riemann surface is actually constant. So this turns out to be. Huh?
Okay.
What's that? Any holomorphic function on a compact Riemann surface is constant. So there's nothing. So it's a system. What?
Yeah,
That's
because
Huh?
That's cool.
That's really cool. Yeah.
Yeah.
I'll just prove it now. Yeah. I mean, this is one of the things that makes Riemann surface theory kick, basically. Makes it such a beautiful theory. I mean, this is beginning, but
like
now what about infinity? In infinity now I have to use another result. Because this is holomorphic, so basically, you see, when you do this, you have checked that this function is holomorphic at all points except infinity, because I didn't check for infinity. But infinity is okay because of this result that we will prove again, that sums of orders is equal to 0. So if you check it at all other points, that's at infinity is also checked. I agree this is a bit of a fast argument, but this is something that.
F equal to R?
F is equal to basically some constant times R. Because the quotient is constant, so this is. Okay, but I mean, this is something of kind of maybe think of it as an advertisement of things to come, if you want. Yeah, so. Okay, so now a little more formal argument. So let me just see what I want to do. Okay, so yes. Yeah, so there is this strange thing, it's called harmonic functions. So if you have a function f from U open inside C to C, this is called harmonic if it has second partial derivatives and satisfies this equation fxx plus fyy equal to 0 on U. Right? This is the definition of harmonic, being harmonic function. So this is a very important class of functions, you know, that they have amazing properties. And actually, these are kind of little brothers of holomorphic functions, if you want, because from holomorphic functions you can cook up harmonics, and from harmonics also you can cook up holomorphic functions. So this is more or less on the same footing with harmonic functions, with holomorphic functions. Anyhow, so you have this. Now, these harmonic functions have a strange, have a very, very peculiar property that if you have a holomorphic map like F from U to V, holomorphic, so V is also open in C. You have holomorphic, and if you have a function F here to C, this is harmonic. Then it follows that if you compose this function with this function, F composed with F, this is harmonic on U. So what we say is that the pullback of harmonic functions on the holomorphic functions is harmonic. So that's something you can so let me write it. Pullback of harmonic functions. Pullback of harmonic functions by holomorphic maps is or maybe I should say R harmonic. Okay. I mean, this is really a calculus problem now because it's just an exercise with partial derivatives. You can just write. I mean, this follows from Cauchy-Riemann equations. Use e.g. CR equations. This is completely a calculus problem, but it's extremely important for applications and all these things. So. Okay, now this, if you think about it, because it's so the harmonicity is preserved under pullback by holomorphic maps. This means that I can define harmonic functions on Riemann surfaces. You just go to one coordinate system, you verify that it is harmonic in that coordinate system, then you are guaranteed that your definition is well defined, right? So for F from U inside X, a Riemann surface to C, so-called F harmonic if for any coordinate chart U and phi, phi inverse composed with F is harmonic. So if you know a little bit differential geometry, maybe Riemannian geometry, you would appreciate this result much more, because usually in geometry, to define harmonic functions over curved spaces, you need a Riemannian metric, right? But in this case, in dimension 2, we don't need a Riemannian metric. It's actually kind of defined in a kind of God-given way on the Riemann surface. So it's independent of choice of holomorphic coordinates. This is something to bear in mind, just harmonic functions. We'll come back to that, use them a lot later on. Okay, so now there are a couple of properties of holomorphic. Any questions, by the way? Okay, so a couple of properties of holomorphic functions that we need. Okay. So one is discreteness of zeros and poles of a meromorphic function. So if you have a Riemann surface, this X need not be compact, right? So if you have a meromorphic function on X, then its set of zeros form a discrete subset of X, and set of poles also form a discrete subset of X. And this comes from the property of corresponding properties on meromorphic functions on C. So follows from the following thing: if you have a function f from U inside C to C, meromorphic, its set of zeros and poles of this guy is discrete, unless it is constantly equal to infinity or zero, unless f is equal to zero or infinity. And of course, I'm assuming U is connected here. You see, I mean, the reason is that if you have a C, I don't know, so this is, I mean, so if, for example, let's look at the case for zero. If you have zero here, and if you have a sequence of zeros that are converging to this point, then this function has to be zero everywhere on this. So this is something that you learn in complex analysis. The same thing goes with both poles. So certainly these things are discrete. So the corollary is that if X compact, again, F for a non-constant, the set of zeros and poles is a finite set. This is the case. This is the discreteness. Also, there is something called identity theorem for holomorphic functions. Again, this is quite strange. That has no real smooth analog. So if you have two functions, so we have f and g going from X to C, and f holomorphic, and f is equal to g on a set which has a limit point. But then this implies that f is equal to g on x. So if you have two holomorphic functions that coincide in some discrete set of points where there's a limit point for that set, then this is it. Okay, so identity theorem, discreteness of zeros and poles. And then now we have something which is we have two also. We need two fundamental results again from complex analysis that we'll use. So one of them is called the maximum modulus principle. So let f from U inside C, again open to C, be holomorphic. And U connected. Of course, connected open subset as always. Now, if there is a point belonging to U such that absolute value of f of z0 is bigger than or equal to absolute value of f of z for all z belonging to U, right? Just for that. Then it follows that f is actually constant. It's maximum modulus principle.
It's open, right?
Of course, I mean, it's always open because I'm talking about holomorphic functions. I can only define open sets. Yeah. Open and connected, yeah. Because if it is not connected, you can have one open set here, one open set there, and this is 0 and this is 1. So, and then the maximum is obtained on that one, but it's not constant.
Yeah, there's like another statement of this is that if this happens, then the point is on the boundary. But like now.
Yeah, but we are not talking about boundary. But basically, yeah, I think that's correct. Yeah, I mean the maximum tends to be on the boundary. So these sort of functions are actually hard to visualize. Functions which are like that, so they're kind of hard to visualize. But yeah, we'll see. Yeah. Okay, so that's maximum modulus principle. You know a great application of maximum modulus principle, right? In complex analysis, you have seen when this is proved, there is one application immediately given to you, right? Right? Answer? What is the application?
Riemann?
Huh?
Riemann?
Liouville's theorem.
You can.
Yes.
I think that's a question, yes,
Yeah. Maybe I'm not sure, but there's an immediate application.
He's trying to prove the, what is that?
A great application is fundamental theorem of algebra. Huh? Yeah, the fundamental, exactly, fundamental theorem of algebra. Yeah, so the corollary of this is fundamental theorem of algebra. So the idea is that if you have a polynomial p of z, right? If you have a polynomial like p of z, which is different from 0 for all z belonging to C, right? You look at 1 over p of z. You look at this polynomial 1 over p, which is a holomorphic function on C, right? It's a holomorphic function on C. And so now you see that at infinity, this goes to 0. This easy estimate. This is like 1 over Zn, essentially. So it goes to 0. So if you just then look at a large enough compact set on the large enough disk, then it's going to attain a maximum there, and that's going to be the whole maximum. Okay? So then this function is going to obtain its maximum somewhere in the interior of your open set, and that maximum, but it means that this is constant. But this function is obviously not constant. That's the proof. So so this is the proof actually that was given by D'Alembert. So let me give you a little bit of historical anecdote here. So this was given essentially by D'Alembert around 1850s. I mean, he didn't use this language, he used a different language, but basically that's one. So that's why French always call this fundamental theorem of algebra D'Alembert's theorem. But when Gauss wrote his thesis, he gave a proof of this. He criticized D'Alembert. I mean, the criticism of D'Alembert is actually is really just minor issue for D'Alembert. Exactly this existence of maximum for this compact sets, basically, which is kind of obvious. But then Gauss gave, I don't know, a couple of proofs. All his proofs actually suffer much more criticism than D'Alembert's proof. But as a result, the rest of the world called this Gauss's theorem. Nobody believes that this was proved actually 50 years earlier by D'Alembert, but that's.
Wasn't it known back then that continuous function on compact sets had maximum?
No, these things are no, they were obvious to them. So the attitude was different. Of course, I mean, they had a very natural feeling for these things. So then what happened in 19th century was that they actually went on and proved these things rigorously. And that was called arithmetization of analysis, mainly making analysis on solid logical foundations rather than geometric, intuitive, physical arguments. Anyhow, so this was a side remark. So this is maximum modulus principle. Okay, so now from this maximum modulus principle we can prove this. So now this also holds.
And does same for like proving the fundamental theorem of algebra, like when we form the 1/3 of z function, we can exactly use the Abel's theorem with a little different.
They're the same. They're the same. Yeah, they're the same. Yeah, they're the
Is
same.
there like a connection between the Abel's theorem and maximum?
I believe so. Yeah, I think you can also use that. I mean, although I'm not 100% sure now. I'm not thinking correctly now. So yeah, we'll over the break we can discuss this. Yeah. Okay. Now, so then same holds for F. So you have from U inside some Riemann surface to C holomorphic plus U connected. I mean, you can use this result, which is in the plane, to bring it over to Riemann surfaces, and then the same statement, so you can easily prove that it holds. Okay, holomorphic plus U. Okay, now, okay, so now we can actually prove the theorem that I mentioned. If f from x to c is holomorphic, and x is compact, this implies that f is constant. So on compact Riemann surfaces, there are no holomorphic functions, except constant ones. Right? When we prove, just use maximum modulus principle. Why we can use maximum modulus principle? Because this, if you look at the function absolute value of f of z, is a continuous function on this compact set, so it's going to attain some point its maximum, and so it has to be constant.
But like aren't compact sets closed as well? So if they're closed,
But they're open also. I mean, the whole X is also open, so there's no problem. There are no boundaries. These Riemann surfaces have no boundary.
What's the problem if we consider, for example, f of z equals z squared on the square from on the closed disk, for example?
On the boundary,
Yeah.
that's not the Riemann surface. The boundary violates
right.
the connection. So the surfaces with boundary are not, are not for, I mean, there is a theory of Riemann surfaces with boundary, but that's, something else.
Thank you.
Yeah, in that case, yeah. No, that's good. So this is really a great result because, it means that to study functions on Riemann surfaces, we have to look at meromorphic functions as a source of functions, and also differential forms. So this will come soon. So differential forms. We use differential forms to construct meromorphic functions. I mean, so we'll see that. So there are no holomorphic functions on compact Riemann surfaces except constant ones. So which is completely boring. Okay. Okay. Now then what? Then okay, so now let's look at another example. So meromorphic functions. On P1. You see, P1, we know that it's isomorphic to C hat. But it's we defined it as projective line. We gave a different definition, right? So this is projective line, right? So do you remember how we defined the P1, the projective line? How did we define the projective line? We define it as the set of one-dimensional subspaces of C2, or basically C2 take away 0 divided by C star as equivalence class. So basically through its homogeneous coordinates, right? Oh, so let me introduce two coordinates, Z and W, where ZW is equal to lambda Z, lambda W, and both of them cannot be 0. Okay, so we define this projective line like that. So now in this picture, if you want to define a function on this P1, how would you do that? How would you approach defining a function on P1? So here's an idea which is very important. So we just define now a function for a point on P1 with homogeneous coordinates Z and W. We just write it as P of ZW over Q of ZW, where P and Q belong to polynomial rings in two variables, Z and W, and these are homogeneous functions. And they have the same degree. That's very important. And same degree. They have the same degree. For example, degree D. Okay. So now look, why this defines a function? So well, P of Z and W, if you have some point with just going, so you see the thing that you have to check is that what happens to P of lambda Z, lambda W divided by Q of lambda Z, lambda W. But because this has degree D, this becomes lambda to the power D P of ZW divided by lambda to the power D P of Z and W. So they cancel, and this is well defined. So that's the power of homogeneity. So as a function on the projective line, this is defined. And actually, the same more or less argument that we gave for C hat, it shows that all basically meromorphic functions on P1 are of this form. Now, here is something very, very interesting. If you are interested in maybe algebraic geometry or number theory, this should be of interest to you. So if you take a Riemann surface X, now just to be on the safe side, let's assume it's compact. Then you can look at M of X. This is the set of all meromorphic functions on X. Okay, the way that I define meromorphic functions kind of excludes the zero, so I just add the zero to this as well. Now, this is a field. M of X is a field.
X with 0.
What's that?
Meromorphic functions on X with 0.
X?
Is that a union? Yeah.
That's what I meant. Okay, so is it clear to you that if you have a meromorphic function, then the sum of two meromorphic functions is meromorphic, product of meromorphic functions is also meromorphic, but then also inverse of a meromorphic function is also meromorphic, because then the poles and zeros get reversed. That's basically what it is, right? So 1 over F is also meromorphic function. So all the field axioms are satisfied for this. I mean, so let's look at one example, which we already know. What is an example that you know already, which is?
Example for what? For
Yeah, for this field. You already know this field in one example, I'm saying. Yeah, for X equal to C hat, right? This field of rational, this field of meromorphic functions, I said that all meromorphic functions are just rational functions. So this is the rational field. So this is C. I don't know what's the notation for rational field. Is it this?
Yeah, I think so.
Okay, so this is the set of P of Z over Q of Z. As okay, so yeah. Okay. So we already know it most. So now you may ask, okay, so what is this field in the next case, which is like an elliptic curve, right? What is that?
Let's see, if one y through p function and its derivative.
Yeah, that's right. That's right. So we'll do that. No, you'll be an expert on this very soon. Don't worry. So it's going to be a field. So it's going to be actually an extension field of this. So I mean, this guy, M of C. So it's going to be a finite extension actually over this one. It's going to be finite extension. And the generator, for example, you can take Weierstrass P function. Actually, the equation is very simple. It's an equation of the elliptic curve. So we'll see that. Wait. Okay, so this has what is the degree? It's degree is a degree 2 extension. So it is a transcendental extension. but it's a degree 2 extension over this infinite field itself. It is a transcendental extension. And the generator, you can say, is the Weierstrass function.
Extension is infinite.
Sorry?
If it's a transcendental extension, isn't it an infinite?
As a vector space?
Yeah.
Yes, absolutely.
So how is it a degree 2 extension?
Hmm?
How is
Oh,
it?
it's a degree 2 extension of this. When you say something is a transcendental extension, you have to define, isn't it? Essentially, for example, K, it means that after you're adding one free generator, then is a finite extension after that. Yeah. Okay, so but but then now you might imagine, so what is this? And go on. So you have infinite number of these interesting fields that you want to study. These are generated by modular forms, essentially, and modular functions. So of all kinds, but I don't think we know all of them actually, but we know some. Okay, so now, by the way, this extension comes from a ramified covering map, which we'll discuss actually soon. So this comes from a map which goes like this. We construct a map from here into sphere. So it's a degree 2 map. Ramified cover. But okay, so this doesn't have to make sense for you now, but you will soon see. Okay, so this is the connection with field theory, with Galois theory, with number theory. I mean, more or less, or kind of beginning of. You can see some. You have to have some picture now, I think, in mind. What is the? Any questions? You're not asking too many questions.
Yeah.
That's too bad. You should ask questions.
I didn't understand why it's degree 2 extension and transcendental at the same time.
You don't have to understand it. That's the point. I didn't give the reason for that to be true. I just said this is the case. I gave you the fact, the end result of maybe 100 years of investigation. So it came to that. But I will justify this. We'll justify that soon, actually. Yeah, but that was a good point. Yeah. Any other questions?
Is there a Galois correspondence between coverings, and meromorphic fields?
Absolutely, yeah. Actually, there is a way of approaching Riemann surfaces completely algebraically. This is essentially the theory of finite extensions of rational functions. That's it. So there is an article by Dedekind and Weber in 1880s where they wrote everything in the language of extensions of field of rational functions. Yeah, so then they show how to recover the Riemann surface by looking at what's it called, evaluations, which we'll study also in some sense now. Actually. Good question. Any other questions? Comments? Demands? Complaints? Okay, so let's stop now and then we will